Okay, the next part of our modern physics unit is going to be the Compton effect, which is very, very much like photoelectric effect. Light this time hits a free electron, not an electron that's bound to the surface. And a new photon is created. So a picture of it's going to look like this. Okay, we have the first photon coming in there, photon 1. It's my free electron. Free electron goes flying this way, and it makes a new photon going over here. And just like the photoelectric effect, energy is going to be conserved. So the photon's going to give up all its energy to the electron, and anything that's left over is going to go to that new photon. So I can see energy is conserved. So the energy of photon 1 brings in the kinetic energy of the electron and the energy of the second photon. Now what Compton realized is this is a collision. And normally for collisions, okay, we do conservation of momentum. So the momentum of photon 1 splits up into the momentum of the electron plus the momentum of the second photon. So the odd thing is how can a photon of light, which has no mass, have momentum with no mass? And what Compton figured out is that the momentum is related to the frequency or the wavelength using this equation. Momentum of photon, we're not going to do m times v. We're going to do h over wavelength. We have an example of this on the next page. You got a photon, hitting a free electron. After collision, the electron has an energy of 1 times 10 to the minus 19. So, like I said, I like to draw a little sketch. So here's photon 1. We have that its wavelength is 6 times 10 to the minus 7 meters. It's going to hit this electron. And right now, we haven't really talked about the second photon, so I'm not going to draw it just yet. But it does say that this goes off with a kinetic energy of 1 times 10 to the minus 19 joules. And letter I up here says, what is the energy of the instant photon? We're going to do E equals hc lambda, 6.63 times 10 to the minus 34 for h, 3 times 10 to the 8 for c. And we're going to divide it by the wavelength, which is given 6 times 10 to the minus 7. So we get the energy of the first photon, d, 3.32 times 10 to the minus 19 joules. Part 2. Okay, it says how do we know a second photon must be emitted? Because energy must be conserved. Right now, the energy of the photon does not equal the kinetic energy of the electron, so there must be other energy around, and it's in the second photon. So I might as well draw that in there. Okay, we got the second photon. It's going to come out like that. And then we want to find its wavelength. In order to find its wavelength, first we have to find its energy. That's going to be pretty easy. Okay? The energy of the first photon gets split up into the kinetic energy of the electron plus the energy of the second photon. So if I just subtract, I will get the energy of the second photon. So the energy of the second photon is going to equal 3.32 minus 1 times 10 to the minus 19. So that's just going to give you 2.32 times 10 to the minus 19. joules for the energy of the second photon. Now, I was interested in finding the wavelength, so then I can use this equation again to find it. So 2.32 times 10 to the minus 19. H again is 6.63 times 10 to the minus 34th. Times 3 times 10 to the 8th for C, divided by the wavelength. And after I do my algebra and plug the numbers into the calculator, I'm going to get the wavelength for the second one. 8.57 times 10 to the minus 7th meters. And notice something, that wavelength is a little longer than the first wavelength. The first wavelength was 6 times 10 to the minus 7. And it always has to be a longer wavelength, because longer wavelength is lower frequency is less energy. And some of the energy went into the electron. All right, our last step is finding the momentum of that second photon. So we'll use that new equation, lambda, 6.63 times 10 to the minus 34th, divided by 8.57 times 10 to the minus 7th. We end up with a momentum of 7.73 times 10 to the minus 23rd. Our unit for momentum, usually we get it by doing mass times velocity, so it would still have the same units. And that is a tiny, tiny momentum, right? 10 to the minus 23rd is going to be a very, very small momentum. But that makes sense because it's a little tiny particle of light. You don't get knocked over by light. Light does not have a large momentum.